Hello and welcome to today's seminar in the Smart Mobility Connection series. My name is Hajar Shahab and I am the Traffic 21 Women in Transportation Fellow. The Smart Mobility Connection series is sponsored by the Traffic 21 Institute and the Mobility 21 University Transportation Center as an opportunity for faculty to showcase their current transportation projects. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note this session is being recorded and all participants' microphones are muted. To ask a question, please send a message through the chat box. You do not need to wait until the end of the presentation to send your questions. Now I'd like to introduce today's speaker. Ümit Özgüner received his PhD degree from the University of Illinois and has worked at IBM Research, Yorktown Heights, Istanbul Technical University, and the Ohio State University. He has spent sabbaticals at Ohio Aerospace Institute and Ford Motor Company. He's a professor of electrical and computer engineering at OSU and holds the title of TRC Inc. Chair on ITS. Starting in October 2013, he became the director of the OSU Crash Imminent Safety University Transportation Center. Professor Özgüner's research interests are in large-scale systems, decentralized control, intelligent transportation systems, and autonomous vehicles. He has over 400 publications and has advised over 25 students on their PhD studies. Please help me welcome Ümit Özgüner as he tells us about his University Transportation Center project, research on pedestrian vehicle interaction.
Thank you, Ajra. Let's see, share screen. Okay, is my screen?
Yes, it is.
It is. Okay, sounds good. Well, thank you for the introduction, and it's a pleasure being here, and it's a pleasure being part of this UTC, and under which we have spent a number of years in looking at pedestrian vehicle interaction. I would say that this is a group effort. There are a couple of faculty members and research scientists and a number of students that have contributed. Dr. Dongfang Yang has finished his PhD, obviously, and has been sort of the driving force of a lot of the research that I'll be talking about, although a number of other students, some of whom have received their master's degrees, have also participated and looked at different aspects of this topic. And we've had one visiting student from Germany also that participated just starting a few weeks before the pandemic struck. And then she hurriedly went back to Germany, but we have continued collaborating with her and have a couple of publications jointly with her and our students here. Okay, let's get into the topic first, and as usual, start off with some slide that we're getting used to looking at how percentages are going, and this is again percentage of total fatalities with pedestrians and traffic, and you can see that it doesn't seem to be going downward. So this is an important issue, and one of the reasons we're interested. I would like to kind of classify a couple of different aspects, I guess, of the pedestrian vehicle interaction. And we're interested in pedestrian crowds and what we call shared spaces, where the vehicle can be sort of moving within the crowd, presumably slowly, and has sort of different aspects of the problem there. And then we're interested, of course, in individual pedestrians crossing the street. And there are some different issues that come up there, whether it's a straight road or whether we're turning a corner and there happens to be a pedestrian there, and so on. Okay, in all of this, the common aspect is the individual pedestrian's motion. And so we started off even before this UTC in having an interest in motion modeling of pedestrians and group of pedestrians. And there, as you can see from that little sketch, we have what we call the ego pedestrian, the one that we're really interested in, and possibly other pedestrians also moving around that presumably you don't want to hit necessarily, and some of them may be moving with you, and then a vehicle, let's say a car, approaching you. So we're interested in this, and if we are looking for number of pedestrians, we have to also think about the collective pedestrians with multiple pedestrians that coexist, where you have a model that's applied to each person, and then you have to also model the interactions. And then when you have a vehicle approaching this group, you have the vehicle influence, then of course the pedestrians behave differently. So I'll spend some time in looking at that specific problem. And I want to show again right here where you see a few vehicles that are trying to move within this large crowd. And of course, this is somewhat of a different problem, although we're talking about a pedestrian that has somewhat similar, if not exactly the same, dynamic capabilities. There are a whole number of pictures that can bring up in looking at these, and even in a lot of simulation models have been produced in commercial domain, although I'm not sure whether all of this is backed up by real data. So we first started getting interested in the mathematical model, and we picked up what has been called the social force model, which is kind of a point mass on the plane type of model, but then where you're interested in the position and velocity and acceleration of your individual pedestrian that is moving around. And then you have social forces, which is a virtual force conceptualized to describe the action taken by the pedestrian, and the action consists of desire to reach the destination and a reaction to the surrounding agents. And the surrounding agents are other pedestrians, and in this case, maybe vehicles. Okay, I'll skip over a lot of this, except I'd like to point out that yes, we can put together all the mathematics of this, but then you don't know whether it fits in with real pedestrian behavior, crowd behavior in the real world. So we started looking at real data, some of which we generated, and then some of which with other people generated. But we were sort of instrumental in generating 2 data sets, and the addresses there. Due to time constraints, I won't try to link to this, but I do recommend that you look at our 2 data sets, the CITR data sets, which is sort of directed pedestrians on our Ohio State University campus near our lab, And the DUT data set, which was done by a postdoc that worked with us and then went back to China, and he did some data collection of pedestrians with vehicles going through them, which we have used a lot, and you'll see pictures of it, and you can get to this data sets if you wish. So this is our experiment on the OSU campus, where we had a vehicle, an automated golf cart, and that went through a number of pedestrian groups walking around and sort of entered their domain. And these are pictures from our colleague now back in China that he has collected, and certainly this is more natural, and certainly has a lot more pedestrians with cars moving. And of course, as you can probably observe, these pedestrians each have been their dynamics have been observed and identified and labeled, and we can actually, simulate and get very similar motion with them. So, and we have created trajectory data sets from what you have seen, and use those in verifying the equations, so that we can now claim that we can model things like this. And I won't go that much into the models and the various parameters. Rest assured that these do exist, and you can read them, and the various forces that we feel are there, a repulsive force, a navigational force, which is proactive, and various effects of these pedestrians moving around, goes on and on. And let me get to the point that I want to make, which is the effect of the vehicle. We do claim that there is a repulsive force due to acting on each individual pedestrian due to an approaching vehicle. And here the approaching vehicle is what you see, sort of the darkest. The vehicle location center of gravity is there. The vehicle is moving, and ahead of it is what we predict is a domain where it will be occupying, and then it does have an effect all over the colored region, and the effect gradually diminishes as you are further away. And of course, the effect is more in the direction of the perceived or true moving direction of the vehicle. So this acts as a virtual force on each individual pedestrian. And pedestrian, we can have various ways that the pedestrian wants to move, and various ways that the car is moving, and see how it will affect each pedestrian's motion. Okay, and we have used set up various parameters in all our modeling, and tried to verify them with all the data that we could correct. So we have a data-based evaluation and baseline models that will cover all these various data sets that we have generated here or in China, or we have obtained when they're available, for example, from Hamburg-Bergdorf Station data set. Okay, so we have identified a few basic motions of both the vehicle moving and the pedestrians moving, and what direction that each one is traveling with respect to each other, and classified them. and have generated a number of simulation-based scenarios to evaluate all these motions, and they're seen there in sort of colorful little charts, colorful little graphs, and I'll try to show you some actual moving versions of these. Okay, so these are all simulation-based results, but the parameters have been verified with real. And we start off by looking at two groups of pedestrians, each one going in a different direction, and they sort of intermingle as and try not to hit each other. And there are certain groupings of a couple of people who want to stick close to each other. Could be a parent and child, could be just a group of friends and that sort of thing. Okay. So now let's throw in a car into this where they all converge at a certain point, and obviously due to the model that we have developed, we can see that the car's emergence affects all the motions, but overall the green guys want to go somewhere, the red guys want to go somewhere else, and they interact and of course make space for the car. And you can try also different scenarios with multiple cars maybe. And the human beings do try to accommodate the cars and sort of use the fact that there are gaps between the cars in passing through. Okay, I'll try to go through this fairly quickly, and just pointing out that we have, tried to collect more data and look at how all of these would behave in real situations, also here in town in Columbus. So we have looked at specific locations in the city of Columbus and checked how these would apply as far as estimating how these would move. And as you can see here, this now is getting to be much more complex pedestrian groups in kind of the shopping mall area, where we anticipate that these sorts of automated vehicles may be moving in spite of all the pedestrians. And this is a simulation with about 40 pedestrians. And obviously you can keep on adding pedestrians and keep on adding cars that move among them. So you can create, traffic efficiency by looking at all the data that you generated and try to see how the effect of these cars of these pedestrians are going to be on the traffic that wants to go through the pedestrians, and do various other studies related to traffic where when you have these common spaces that both human beings and vehicles have to use at the same time. So we have done a basic simulation model, created a model, but we're getting into more and more complex scenarios and trying to use this as an analysis tool. Okay, so in the remaining time I want to, which is not too much, I'd like to look at sort of a different problem. Once you have the pedestrian model, you can get into a whole bunch of other issues too. And so let's leave the crowd problem aside and just simply look at a pedestrian trying to cross the street and use the same sort of models that we have generated. And again, since you have seen sort of almost 6, I believe, different students working on these type of things, we have covered a lot of different types of problems and settings and scenarios that you may be interested in. And I'm just going to talk about a couple of them. And mind you, we have looked at various other scenarios, various other situations that you might be interested in. Of course, one very simple case is just one pedestrian trying to cross the street and a car approaching. Now, so far, we have kind of assumed in what I presented that the car itself does not do much decision making. It's slowly driving through a crowd or crossing paths with a single pedestrian, and it just keeps on moving. Now we're and we try to see what the pedestrians might be doing. Now we'll try to look at it from the other viewpoint, from the viewpoint of the car, and let's start with how the car is going to possibly make a decision about slowing down and making a decision about stopping to let the pedestrian live, basically. So again, we can go through lots of different types of modeling, and as I pointed out, there are decisions being made, observations that are being made from the vehicle side, and there are observations made by the pedestrian side. And as the pedestrian moves forward in a setup like the one that I just showed, the pedestrian will do gap estimation, can use his social force interaction model, and then will affect the pedestrian dynamic model. And the vehicle will have a pedestrian motion predictor and has its longitudinal speed control and the vehicle dynamics. So the pedestrian dynamics affect the perception of the pedestrian motion in the vehicle. The vehicle dynamics affects the pedestrian's gap estimation as it tries to cross the street. So this is the type of framework that we have established and worked on with different scenarios. Again, I won't go too much into detail. We'd be happy to answer questions, or you can get in touch with me after the presentation. But again, as you may guess, there are various decisions being made looking at various thresholds. Okay, getting close to wrapping up. So I'll skip over those slides. And again, now you can have more detailed version of the car's behavior as the pedestrian crosses the street. And you can see the car maybe slowing down, maybe stopping, or not. And hopefully the pedestrian can decide whether it should be moving, and hopefully this won't occur. I'll quickly go over another student's work just to give you a taste of what other problems may arise. If you have a situation like either the one on the left where there are trees on, well, in this case, both sides of the road, and there could be pedestrians hiding behind the trees that are occluded, or on a street where you have parked cars like this with pedestrians possibly thinking about passing, and however they would be occluded from the vehicle's viewpoint because of all these parked cars. So there is an occlusion risk, and the car itself or the driver has to decide what the probability is that a pedestrian may emerge behind the car. So we have looked at extensively, in fact, sort of parked cars by the side of the road behind which pedestrians may be emerging, and investigated what the probability distribution of one or more pedestrians emerging behind these cars are, depending on multiple cars being there. Of course, in a situation like this, there may be other information about what is, further behind in the source of pedestrians coming. Is there a sports field that people were watching the game? Is there maybe a high school and this is the doors opening at the end of the school day? So there may be sort of background effects that can give you more cues about the possibility of emergent pedestrians. So we are interested in evaluating those types of cues, possibly in an intelligence AI type of setting, and maybe even learning about these things. But the point is, there is going to be a certain probability distribution along this roadway of emergent pedestrians. And we can certainly base our decisions on that. So again, you can do a risk assessment and this sort of thing, depending on what your assumed pedestrian emergence probability distributions could be, and make your speed determination for the car based on our knowledge of, yeah, somebody could be jumping out from behind the car, or maybe just see the pedestrian there anyway with cues. Okay. Again, for lack of time, I won't be going too much into detail, just trying to give a taste of the different types of problems that one can try to model, try to understand, and try to act on, especially if you are thinking about having an automated car drive along a roadway where there are parked cars and the possibility of pedestrians jumping out who are occluded, but maybe coming out behind those cars. And you can decide on whether you need to yield, whether you need to decelerate very rapidly, whether you want to do a cautious drive along this road, and decide on that beforehand. Okay, so we have established some baselines, trying to see if I have any simulation that I can show you. Again, here's a simulation of various possibilities of emergent pedestrians. And here's the possibility of a crash occurring. Okay, let's go to another slide. Okay, here's a case where the car really slows down because he sees the pedestrian sort of kind of out in the open there. And here is just a cautious drive. And obviously, there is a pedestrian crossing there where the probability of a pedestrian crossing the street is higher, but that doesn't mean that there may be pedestrians jumping out behind these cars onto the roadway. And various other cases have been studied. Let's see, let's start that. Going across, and what we're looking at is different cases where different types of driver behavior obviously can affect the outcome, i.e., whether there is going to be a crash or not. So I won't go into many more, but just, as I said, give you a taste of what has happened. Okay, let's see. So in the end, you can decide on whether you want an automated car that has how much risk would it take? And you decide it has to be very cautious. Of course, it'll take a long time. If you wish that you'll never do emergency braking, then it will take a long time to go to travel along that roadway with multiple parked cars. Or if you want to allow it to do somewhat of a jerky motion, not entirely jerky, but slowing down, speeding up again, etc., then you may take less time to cross that, depending on the probability of looking at different cues. Okay, and we have proposed an algorithm, and that looks at occluded unseen pedestrians in scenarios. Okay, we are continuing work on this aspect and looking at different types of sensors and the effects and so on. And as I keep on saying, I'm just trying to give sort of a taste of the different types of issues. Just a couple of minutes, we are doing a lot of work on intersections with vehicles turning. Don't mind the fact that the vehicle is on the left lane. This is a study related to data from Japan, where you're turning from the left lane into the left lane, and you're sort of interested in whether there's a possibility of hitting a pedestrian that's just around the curve. So we have done a number of studies in these sorts of things, and also looked at possibility of new technologies like having sensors looking at possible pedestrian crossing the street and providing information to the car about that pedestrian and how safe it is to turn this corner. And obviously this is a nice clean figure. In real life, take a look at the photograph here, where the occluded pedestrian can be right behind this bus stop, and it could be right behind this bus on the left. Either one could be just running out in front of us. So there is a ways to go between a clean, modelable setup like that and a real life situation like that. And we understand that, but we're trying to understand also and establish what the basics are and what we should be looking for in designing automated driving systems. Okay. Again, a lot of investigations in the following type of scenario where our sensor may or may not be able to see, and at some point we'll see, if we're going to make a turn, it will see this pedestrian at some point, whereas if there is a V2V connection or a V2X connection, right, we can learn about the pedestrian that is crossing. Okay, and again, you can build models that include the speed of the pedestrian, communication range, detection range, and things like that. And let me just throw one simulation of a car coming and hitting the poor pedestrian. Okay. At some point, we have to stop, but I think I covered a whole bunch of situations. All I can say at the end is there's much more work to be done, especially once you get into designing automated cars that may be either slowly moving among crowds or just having to deal with occluded but emergent pedestrians for which we have to slow down and stop. So much more work to be done, but it has been interesting work. So I think I'll stop there since I was told to do maybe about half an hour, and see if you have any questions and points you want to bring up. Thank you.
I have a question.
Yeah.
Very interesting presentation. When designing automated driving systems, what are the top 2 or 3 challenges that still need to be done for designing safe interaction with pedestrians?
Well, that's a hard question, of course. It's a great question. It is the question. We like to, I mean, I would like to see more information, especially in the emergent case. And right now, what we are looking at is there some additional sources of information that normally a human being might be using. I mean, if you are approaching a bunch of parked cars, and you have in your mind as a human driver what the chances are of people jumping out at you. You may be using other information that's not clear, which could be, do you see emergent people in the buildings behind? Or do you see maybe a school or a football field? I showed you a picture of a bus on the left side as I'm driving by. Now, if that's a bus stop on the left side, totally unrelated to me maybe, but there is a chance that a pedestrian may be rushing across the street to catch that bus. So that's the type of additional information that a human being, human driver, maybe almost subconsciously be aware of, and make decisions to be more careful and maybe drive slowly. That's what I think may be of interest to formulate. Because you can say, I want to learn and use some learning algorithm about emergent pedestrians, but can the human being seems to draw different information from things that, you know, when you sit down and try to model, you never think of that. I mean, if you're driving along, how conscious are you of a school whose doors may open and people may rush out? So there are other sources of incidental information, and a human driver may be using, but we don't necessarily consider in our design of automated vehicles. And I think that's one of the issues that has to come up. So is that the most important issue? I don't know whether that's the most important, but it's certainly something, not just for the pedestrian problem, but to build synthetic drivers, let's say, automated vehicles that we have to consider.
Okay. Has any work been done using audio cues from the cars to the people?
I don't know. There certainly is a bunch of results about audio cues. I have not thought about how this is applied in this situation. Certainly, if you're also now, we gave a physical interpretation of the car's body affecting you. Now, remember that with electrical vehicles, the car's engine sound may be non-existent almost, or not audible enough. And that can certainly affect things. In fact, people are talking about just adding sound to electrical vehicles, and that will affect the pedestrian's motion. But we have just use sort of the physical body shape and speed to tell us how the pedestrian may keep away from jumping in front of the car or hitting the car or something. Certainly, if the car blasts some sounds, that will affect, and we haven't modeled that.
Okay. As autonomous vehicles are taught to behave better, will pedestrians be trained to behave more badly, assuming the deference of AVs? Will this hamper the efficiency of the whole system?
Well, I mean, the simple answer is I don't know. Will pedestrians be trained? I doubt that pedestrians will be trained to do anything different. It's really up to us to, as vehicle automation designers, to look at these conditions. Now, if you are going to accept that there are some links, wireless links to individual pedestrians that can provide, look out, there's a car coming type of information to the pedestrian, that's certainly worth thinking about. So certainly when we are talking about a roadside assistance capability to the automated vehicle, that is the camera around the corner type of thing. We've always talked about the car, the intelligent car getting that information. Of course, if you have people to whom information can be provided, that may help too. I doubt that human beings will be trained. We have problems enough with forcing people to get driver's licenses. Walking licenses, I don't think so.
Okay, through your work, what have you found to be the most surprising or unexpected?
Interesting question. I'm surprised every day, especially when you get into behavioral issues, because I feel that as engineers, we don't deal too much about human behavior type of issues, pedestrians being one of them. I was intrigued, and I wouldn't say surprised, because I don't think I have thought about the problem that much, about how people gather together or form groups in walking, and the other issue is the children's behavior and how different it may be from the adults' behavior, and especially with higher technology issues, the wonder is there, whereas humans can get sort of blasé about, so don't care after a while. Oh, okay, there's an automated car, who cares? Yeah, it's always there. Whereas the children, once they sort of notice this robotic car or vehicle going around, keep having their wonder and amazement there, and maybe walk up to it and look at it and get closer to it. So the one thing that I have been surprised with was probably the behavior of how children behave somewhat differently than adults.
Okay, can you share again how people can learn more about your work?
Well, we have links on our to our web pages. You can do a search on Google, my name, and with pedestrians, especially if you're dealing with this pedestrian issue. I don't know if CMU under Mobility 21 provides those links. I believe it does, right, to Ohio State University and my lab.
Okay, as a student interested in a career in research, what is something that you learned during your career that they should know?
Say the last part again. I didn't quite get it.
What is something that you have learned during your career that a student who is interested in a career in research should know?
Well, it should know is you should keep on wondering about things and how things work and why these things happen, and always, you know, open to the new wonder things. I mean, I think of it this way: I'm a retired professor. This is my 6th year after retirement. Yet, sort of a almost a full-time researcher, both at the university and in my company, and all the time I get problems that you say, "Wow, that's interesting." So somebody's flying a helicopter on Mars, or somebody just landed for 15 seconds onto a meteor type thing in space, and then got samples and bounced back again. I mean, you keep on being amazed about all the things going on around you, and that leads you to doing research. I don't know if that answers it.
That's great. That is all the questions that I have.
Well, thank you, everybody. And thanks for the wonderful questions.
Thank you, Amit, for sharing your work, and to all of today's attendees, thank you for joining us. As I mentioned earlier, today's presentation will be posted on the Mobility 21 What's Happening page of the website, along with the link to the video of the session. This afternoon, you will be receiving an email asking you to take a short survey about today's SMC. Please take a few minutes to provide your feedback. For students who are interested in engaging in transportation topics, the Transportation Club on campus is a great way to plug into transportation topics with fellow transport nerds. This has been the final SMC of the spring semester. We will resume meetings in the fall, so please be on the lookout for reminders. Again, thanks for attending today.